Hi, welcome to Chem with Chem. Now in this video, we take you to the beginning of organic chemistry. Yes, an introduction. Stay to the end because after the introduction, we actually look at some of the things that we've learned in our past paper questions. Check it out. Remember to like and share if you find value and consider subscribing if you have not done so so you don't miss any time new content is added. Couple later. Just the way the objectives are written, we can pretty much get some of the information from them. So without going any further, without even starting, we can see where natural gas and petroleum are natural sources of hydrocarbons. And we're going to list the main uses of at least 3 fractions obtained from the fractional distillation of petroleum, also known as crude oil. We're going to today also describe cracking of petroleum fractions. We have 2 types. We have thermal and catalytic cracking. And then they want us to illustrate that carbon can form single and double bonds, branched and unbranched chains, and also ringed compounds. So just do simple illustrations. We should also write formulae to represent simple organic compounds. Not sure if we're going to get as far as that one. List the general characteristics of a homologous series. We're just going to use some of the examples that they have right here to help with those illustrations. So let's get right into it. We said natural gas, over 78% of natural gas is methane. Small amounts of ethane, propane, and butane are present. You'll also find hydrocarbons in crude oil, also known as petroleum, which is a complex mixture of hydrocarbons. It's so complex now that we need to actually reel it out. You can think of it as a series of threads that are knotted together that we have to pull out, but we don't pull them out like that. We use heat, fractional distillation to get them out. And then there is one other source, peat, which is found at the bottom of some mangroves formed from the decomposition of organic matter. So that is a source of hydrocarbon. You'll have some form of natural gas in that as well. When peat breaks down, you get methane, which comes out of the water, comes in contact with the atmosphere, and you end up with spontaneous combustion. This we see on the Black River Safari, for example. Peat is found at like the bottom of mangroves. So when the leaves and all the other materials decay, it forms this substance known as peat, which breaks down to give you methane. So when the methane comes in contact with the air, it bubbles out of the water, comes in contact with the air, you get spontaneous combustion. So you have fire on top of the water. So that tends to be an attraction, or used to be an attraction at on the Black River Safari. I don't know if that's still the case, or on some parts of the Black River. All right, let's know. Cool. All right, so the next one is crude oil fractions and their uses. So at the top of our fractionating column or fractionating tower, column would be in the lab. In real life, you have a big tower just like up by Petrojam. You normally see this with a flame. The tower that you see with the flame is where they have the fractionating tower. At the top of it, we have the lighter fractions. So the different components come off based on volatility. And the shorter ones are more volatile, meaning they have the lower boiling point. So they will evaporate first. Then there's a series of condensation and evaporation, and it keeps going on until it reaches the top. The top of the tower is cooler, so you have them coming off first. So you'll have the refinery gas closer to the top. After that fraction, you have petrol. Then you have what we call naphtha. I've seen a past paper in 2015 that gives carbon 1 to 14. I'm gonna show something similar to that in the next slide. There's a carbon 1 to 14 is refinery gas. They'll also accept cooking gas, but we're not going to look at this right now. All right. The second fraction, petrol. And if you get a question, you just have to look to see how they put it. And then we have naphtha, which is used in chemical production. Then we have kerosene, which is used in jet fuel. Then we have even those with longer chains, diesel oil. And you realize that as you go down, the temperature is actually higher. It's the highest at the bottom where you have bitumen, or the residue, bitumen. So you have diesel, and as you go lower, you have the residue, which we use for, well, fuel for ships, lubricating oils, and also road surfaces. So that is used in the manufacturing of asphalt. All right, so let us see what the fractions look like. So refinery gases, we have carbons 1 to, look at the carbon length. We're focusing on the carbon length. So those are the shorter chain one, carbons 1 to 4. Then the next one we have gasoline or petrol, and we have that from 5 to 8. Then we have naphtha, 8 to 10. Sometimes you don't see naphtha at all, so you'll see gasoline ranging from 5 to 10. Sometimes naphtha is not shown, so you can get away by leaving out naphtha. Then there is kerosene around for carbon 10 to 16, and those are just, even though they say carbon 1 to 4, even in refinery gas you might get a little pentane in it. Where they say gasoline 5 to 8, you might get some chains that have 9 carbons in it. It's a fraction. The cutoff, you might have some spillover in a sense, if you get what I'm saying. So sometimes gasoline smells like kerosene because some of the compounds, that some of the molecules that are in gasoline, they're actually in kerosene. So it's a fraction. So where they say 10 to 15, it's not dead 10. It's not dead 10. You can have some that have 9. So after kerosene, we have diesel. The chain is getting longer, 16 to 20. And then you have heavy fuel oil, 20 to 50. And you have those that are greater than 50, that we call the residue or bitumen, that we use in road surfacing. Note that the viscosity increases as we go down. The chain is getting longer. The intermolecular forces of attraction is increasing as well. And so you find that the boiling point is also increasing. So boiling point increases, viscosity increases, so they don't flow as easily. And the flammability decreases. So the ones at the top, they will burn better. The heavier the fuel, the harder it is to be ignited. All right, just some side notes we can bear in mind. All right. So let's look at some of the uses. We use alkanes, and we look at what alkanes are. That's a member of the homologous series. One of the homologous series. We use them for fuels. We use some of them for precursors in manufacturing of other chemicals. We use them as solvents. For example, pentane is used as a solvent. They also can be used as lubricants. Now, one of the things that the syllabus wants us to look at is the cracking. What is cracking? What happens in cracking? So what we do in cracking, you might end up with a hydrocarbon that is, in cracking, you might have a long chain, the hydrocarbon, that is not so useful because it is long. It can't really burn. It doesn't burn as readily. So you might want to split it into smaller molecules that are more useful, that can be precursors, that can be used as starting materials for other reactions, or something that can burn better. So what we do, we split them. We can split them using a catalyst at high temperature. When we do that, we call it catalytic cracking, or we can just split them using heat. And when you split them using heat, we call that thermal cracking. So you have thermal cracking and you have catalytic cracking. So one of this should just, the thermal one does not use catalyst. So you have catalytic cracking with a catalyst, and then you have thermal where we just use heat. Now, normally whenever we crack an alkane, a long chain alkane, we normally get an alkene at this level. We can just write that we get an alkene, an alkane, and a corresponding alkene. So I know we haven't touched homologous series as yet, but for the alkanes, we might as well just get used to it. The general formula for alkanes is CnH2n plus 2. That's for our alkanes. And for our alkenes, it's CnH2n. So notice here, the number of carbons must add up at the end of the day. So we have a 12 carbon long chain, right? That's duodecane. And when we crack that, which alkane are we getting over this side? C8H18. Which alkane is this? I'm gonna circle it red. Which alkane is this? So we have an alkane and we have an alkene. So this is our alkene, and this is our alkane. So which alkane is this?
Octane.
Octane. Very good. So this is so that's octane, and octane should ring a bell. And the alkene is 1, 2, 3, 4 carbons. Could you say that again?
The butene.
Butene, B-U-T-E-N-E. All right, so we always end up with when we crack our alkane, we end up with an not shorter chain alkane and an alkene. And it could have gone otherwise. It could have we could have gotten a one with 6 carbon. So we could have gotten 6 is hexane. We could have gotten a hexane and hexene. We could have gotten heptane and pentene, 7 plus 5, 12. But at the end of the day, we'd have to get back 12 carbons. All right. Let's see, homologous series. What's a homologous series? That's what we're going to look at next. What's a homologous series? So they're pretty much, they're like a family. So they represent families of organic compounds. Just like how you have a family. My family, the last name of my family is the last name of my family. The last name of your family is the last name of your family. So it's something similar. They even have the same ending name. Just like how we have same last name when we're in a particular family. Or our family name is just our family name. Based on our culture, we get the last name from the what they call that, patrilineal is from the father's lineage or the father's line. So some characteristics, they have the same general formula. So every member of the alkane series will fall under the formula, which is for the alkane series, as we said earlier, CnH2n plus 2, and N represents the number of carbon atoms. So if N equals 1, it means that H would be 2 times 1, 2 plus 2, 4. So the first one would be, not jumping the gun, CH4. Everybody in the alkane series would fit in that. They also have the same functional group, and as a result, similar chemical properties. They have the same name ending, or what we call the last name. So all the alkanes end in ane. All the alkenes end in ene. All the alcohols end in all the organic acids end in anoic acids. That's how it works. And then the other thing, the physical properties, they have physical properties that show a steady variation based on increasing number of carbon atoms. So you'll get the boiling point increasing gradually. You will get the the boiling point increasing gradually as the chain gets longer. The intermolecular force of attraction get stronger, or it increases. So you'll have physical properties that show a steady variation. All right. Now I want us to look at each homologous series. According to the syllabus, we must know how to name the first 6. So we're not going to just name, we're going to name and draw. So we're going to look at alkane, the general formula. We're going to look at the first 6 examples. We won't touch on isomers just yet. We're just going to draw a straight chain. All right, so let's see what this looks like. So alkanes, the general formula, CN, we mentioned it. This is the third time we're mentioning it. CnH2n plus 2, where N represents the number of carbon atom that is present. H represents the hydrogen. So if you know what N is, you can just plug N in the formula. The first one in the group is methane. And the formula, the condensed formula, as it's stated there, is CH4. We could do the displayed formula like this, and that would be fine. That's CH4. We could represent the second one, the display formula, as well for the second one. And in what we're doing at all times, no matter what we do with the carbon, when we're drawing, at all times, carbon must be present in 4 bonds. Carbon is unique. One of the features of it is that it can bond to itself singly. It can bond to itself doubly. It can bond to itself triply, even though we're not going to be looking at any triple bonds. All right, it can form rings. We're looking at anything now that will have any deal with any ring structure, but we're gonna demonstrate that in a little while. All right, propane. If we're to do propane, then we would draw 3 and we dress them up in similar manner. And if we were to draw butane, all we're doing each time we're increasing by a CH2 group. That's what we're doing. So butane, we'll just need to add another CH2. Pentane, we add another CH2. Hexane, we add another CH2. So that's how that will go. And then please note that there is no functional group for the alkanes, and we'll see that they are not as reactive as the alkenes that have a functional group. The alkenes undergo far more reactions than our alkanes. All right. Some books will say it's the carbon single bond, because that's where the reaction takes place, but it's not really counted as a functional group per se. Even though when substitution is taking place, it takes place on a carbon atom, but it's not really counted as a functional group. All right. But what I want you to focus on is the general formula. Sometimes they ask you to state the general formula. All right. Now let us look at the alkenes. General formula, CnH2n. So whatever N is for carbon, the number of hydrogen is just twice that. So it starts at, because it's CnH2n and there's the functional group is a carbon-carbon double bond, it naturally starts at ethene, where you have 2 carbons, because you cannot have 1 carbon doubly bonded to itself. You need 2 carbons. So the first one in the series is ethene, where N is equal to 2. So it would be C2H4, and it's drawn like this. We just put on the hydrogens and we're good. Cool. Propene, we just take our ethene and we add a CH2 to it, and we're good to go. Carbon must at all times be taking part in no more than 4 bonds. 4 bonds. So this is propene. Then we could do butene. And then when we touch butene, we have different places that we could put the carbon-carbon double bond. And that's just another way to say we have isomers. So I'm gonna circle it. kind of jumping the gun, but we could have put the carbon-carbon double bond. Let's call this carbon 1, carbon 2, carbon 3, carbon 4. We could put the carbon-carbon double bond between carbon 2 and carbon 3, and it would still be butene, but we'd call it but2ene. But I'm gonna save that for when we look at isomerism. All right, and what we do each time we add a CH2 each time to the group. So after butene, you'd have pentene, then you would have hexene. All right. The next one is the alcohol group. And we're gonna pause a little bit right after this one. For the alcohol group, note the general formula: CnH2n plus 1 OH. So when n equals 1, we end up with CH3 OH. The OH is the functional group. I normally do it in red. Didn't do it in red this time. Ethanol, we could say C2H5OH as it's written here. Then we draw the display formula, would need 2 carbons. That's ethanol, and we could continue. It's a little intuitive. The one that tends to trick, or the one on which students trip up, tend to be carboxylic acid. But what we need to bear in mind for this one is that though the formula says CnH2n plus 1 COOH, the C in the COOH is actually counted as a part of the formula, right? So if you say n equals 1, you're going to actually end up with at the second one in the series, because the C in the COOH is actually counted. So the first one in the series is HC double bond, well, COOH. It can also be written as this, the displayed formula. Let's take that again. Take that back. COOH. That's the first one, which is methanoic acid. The second one, and this wouldn't be when n equals 2. You cannot say when n equals 2 because the C in the COOH is already a part of it. So the second one would be drawn like this. And of course, notice that in all of these, for all of them, our carbon is taking part. So this is ethanoic acid, or carbons are taking part in 4 bonds, no more than 4 bonds. All right, so gonna pause here for a bit. So we're going to apply some of what we just learned to a question, or a partial question. This is May-June 2019, question 5. Methane is the first member of the alkane homologous series. List 3 general characteristics of a homologous series. All right, good. Similar chemical properties, what else do they have in common? Similar reactivity, that's what was just said. Chemical properties would be the same as reactivity. So go again. Think about another one. All right, so they have the same name ending. We want the molecular formula of the second and third members of the alkane homologous series. So go ahead, put that in the chat, or put that in the comments. So the second one, figure out the name. We haven't gone into how we name them, but this is a revision. So we know that for 1 carbon, it's meth. 2 carbons, eth. 3 carbons, prop. 4, bute. 5, pent. But it's the formula they want. So they want the formula for 1, 2, ethane, and the formula for 1, 2, 3, propane. So the second and third, go ahead. All right, light up 1. So ethane, I'm seeing C2H6 for the second one. And then the third member would be C3H8. So we have C2H6 and C3H8. All we're adding there is a CH2. All right. Then the next thing they want us to do, they want us to derive the general formula of the alkane homologous series. Derive. Do we have to derive it, or can we just tell them? Do we know it? I think we know it. We can just tell them. We mentioned it earlier on. What's the general formula for the alkane homologous series? For 2 marks, we can just write what's happening here. If we look at it, whatever the number of H is, we see that it is 2 times that for carbon plus 2. So we just write CnH2n plus 2. There isn't much derivation there, but because we're expected to know that. This is where we're going next. Okay. 1-butene belongs to the alkene homologous series and exhibits this thing that's called structural isomerism. Define the term structural isomerism. What is meant by the term structural isomerism? This is our revision organic. We're about to touch it just now. Go ahead. So you have the existence of molecules. Try not to use the same words. The existence of organic compounds having the same molecular formula, but different structural formula. You could say different arrangement of the atoms in space. So we'll say, let's go in red. Or you could say existence or occurrence. All right. Then they want us to draw a fully displayed structural formula of 1-butene. Every time I see 1-butene, I'm tempted to just cross it out and put but1 in, because that's really the IUPAC name. We'll do the first one. We'll look at what does but1 in mean, or 1-butene mean. But it's called but is the prefix for 4. So we'll have 4. And then we said that at carbon 1, the first carbon, there is a carbon-carbon double bond. So that's what we would have. Hope you're drawing with me. You have the year, the name of the year paper. Don't just watch, draw with me, study with me. All right. So that's one way we can put it. And when we're doing this, when we're looking for structural isomers, it's like we're playing with Legos and we are trying to find a new way. We're trying to find a way to make something new, or a new structure, a new robot out of a set number of blocks. So that's what we're doing in a case like this. Let's fix this. So they want us to move the carbon-carbon double bond around or change up the arrangement of the molecule each time getting something new. Please note, if we do it like this that I'm doing on the right-hand side, it's not something new. 1, 2, 3, 4. Okay, let's back that up. Does that look like a carbon-carbon double bond? Okay.
Excuse me, sir, I have a question.
Go ahead.
So you know how like they have butte and they have the one in. Does the one tell where the double bond should be?
It's actually telling, yes, it's telling the location of the carbon-carbon double bond. It's saying it's on the first carbon, carbon 1. So, yeah, that's that. These two structures that I've drawn, they're the same thing. So you cannot draw them back and say, hey, there is one. No, these are actually the same thing. All we've done, we've flipped the molecule. We flipped it around. It's like they are mirror images of each other. So those would not be, so these two, let me put equal. That is equal to that. All we've done, we flipped it. Do you see? If we're to count, let's put in some numbers. This is carbon 1, carbon 2, carbon 3, carbon 4. This is carbon 1, carbon 2, carbon 3, carbon 4. They are the same thing, but 1 in. So the other one, the other isomer, where do you think, how do you think would form the other isomer? You have to be very specific when you say you'd move. What about the double bond? Couldn't the double bond go somewhere else? If we were to put the double bond somewhere else, wouldn't that be a new molecule or a different? So far, it's at carbon 1. Couldn't we put it at carbon 2? What if we put it at carbon 2? Let's try it and see what we get. So let's get red again. So 1, 2. So the good thing about this one, whichever end you count from, it's still at carbon 2. Any end you count from, it's at carbon 2. So if we put the carbon-carbon double bond right there, we have the same formula, molecular formula of C4H8. We have that. Isn't that a different structure? Same MF, but different SF. Is that a different arrangement? Whichever side you count from, I want to decorate this. So this is carbon 1, carbon 2, carbon 3, carbon 4. We can also count from the other side, and if we do, we can get carbon 1, carbon 2, carbon 3, carbon 4. Whichever side you count from, you will buck up in a carbon-carbon double bond at carbon number 2. So this one, we would call it, I don't know if they're going to ask us if we should name it. I don't want to preempt the question, but we should be able to name it. If the first one is 1-butene, we could call the second one 2-butene or but-2-ene. Now, is there another way that we could actually get another form of this compound? What could we do to this structure to get something else, something different? Remember, you can pull off and pop and change over position of different things. So we've changed the position of the functional group. So far, it's a straight chain. The next thing we could do, I'm going to take off those numbers, or I'm going to let it stay. I'm going to keep one set of numbers. We could take the CH3 group, that little portion. We could take that little portion right here, this part. We could take this portion and cut it right in the middle of the bond right there. So we have the bond. We could cut it and exchange places with this hydrogen that's in the middle and carbon 2. We could exchange places with those. We could swap places. And if we did that, I'm sure we'd get a new structure. Would get something that looks different. It would have the same number of carbon, the same number of hydrogen, but it would look different. So let's see what that would look like. We'll have carbon. All right, let's put it here. There we go. And we're gonna put on, let's straighten our lines. Each carbon at all times in 4 bonds. So this time around we'd have, they did not ask us for naming them, but let us look at what we've just done. We moved a methyl group. That's a CH3 group. Normally it would be CH4 if it were methane, but it's methane without a hydrogen that you can stick on or attach to something else. So we move the methyl group and we put it on, we switch places with the hydrogen that was actually on carbon 2. So if we're naming, we said this would be called but2-ene or 2-butene. And then this one would be called, the longest chain has 3 carbons. Let's count. Carbon 1, carbon 1, carbon 2, carbon 3. On carbon 3, on carbon 2 in the middle, there's a methyl group that I'm trying to highlight with broken lines. So we'd call this 2 to say that on carbon 2 there's a methyl group. We name what's on carbon 2, 2-methyl, and then we'd have propene. Make sense?
Sir, go back again, please.
All right. We've switched places a while ago. We took the methyl group from that was at carbon 4, and we switched places with the hydrogen that's on carbon 2. Look at isomer 1 and isomer 2. It's just a switching up of the methyl group that's at 4. The arrow is there to show where it went. So in naming, the longest chain is 3 carbons long. So if it's 3, it's prop. The functional group is our carbon-carbon double bond, which is our alkene. So we know that the main name there will be propene, but it has a substituent. There's a group on carbon 2. The middle carbon has the CH3 group, which we call the methyl group. CH3, we call it the methyl group. Right? So we say it is 2 because on carbon 2 there is a methyl group. So carbon 2 is there in the middle, and on it there's a methyl group. So we say 2-methyl, and then the longest chain is propene. So that's what the name would be. Clear?
Yeah.
All right, cool. So we'll move on to the next one. Any questions? What I want you to do, practice drawing them. And I'm going to send you a link that looks at one that has 6 carbons, because the longer the chain is, the longer the chain, the more isomers you have, the more you can cut them up and so on. So when you're watching it, I want you to draw with me, or even pause it to see if you could actually get a different arrangement or what isomer you would actually get next. But it's about drawing. It's about counting from all the different directions so you can see what the longest chain is. Because when we're naming, we name based on the longest chain. All right. So there was a question on the January 2024 paper asking about isomers of hexane. So I went ahead and just did all the isomers of hexane. They wanted 2, we just went ahead and did all of them. So you can check that one out. All right. I'm going to actually send the link. All right. 1-butene, like all alkenes, are described as unsaturated compounds, and they undergo hydrogenation reactions to become saturated. We have not reached reactions of alkenes as yet, but it's something, it's intuitive, it's something we can grasp. So they want us to define the term unsaturated. I know you've heard the term saturated before, but when they say unsaturated, when we say a molecule is unsaturated, what do we mean?
Where not all the bonding sites are occupied.
Not all the
Not all the bonding sites are occupied. Not all the sites are
bonding
occupied.
sites are occupied. What bonding sites are you talking about?
Not under carbon atom.
All right. But they're actually occupied, but it's just the type of bond that is present. Because if I were to draw a saturated, and if I were to draw an unsaturated molecule, you'd notice that the carbon atoms are still involved in 4 bonds, but it's the type of bond that is present. So once we're talking about unsaturated, it means that a carbon-carbon double or carbon triple bond is present. So in other words, the carbons do not have on the maximum number of hydrogens that they can have. You'd have carbon bonded to itself doubly or triply. All right, let's change this color back to red. All right, and then when you look at the word hydrogenation, what is meant by a hydrogenation reaction? Look at the makeup of this word. Look at the etymology. They have hydrogen and they add to the end. They add to the end ation. So what do you think hydrogenation means? What are we adding? What if it were wolfidation? What would that mean? Or better yet, fun and joke
Sir,
aside,
the adding of hydrogen.
the adding of hydrogen. Just like how hydration is the adding of water, hydro coming from water, this one is hydrogenation. So we'll be adding hydrogen. So let us look at what the other one would be. So it's the addition of hydrogen. So we're going to go back to but1-ene. They want us to draw the fully displayed structural formula of the hydrogenation product. But before we get to the product, I want you to see where it would go, where the hydrogen is going to go. So as is, it doesn't have on the maximum number of hydrogen. Its counterpart, butane, would have on the maximum number of hydrogen that it can hold. But the formula for this compound is C4H8, coming from the general formula CnH2n. Now, what we could do to add hydrogen to this, we would need to cut that bond right there, cut the hydrogen in 2, and would add on 1 hydrogen to this carbon, and we'll add the other one to that carbon. So let's look at what the final product would look like. There are conditions for this, but we'll look at it when we look at reactions of organic compounds. We'll look at that in our next class. So the top one is unsaturated. This is 1-butene or but1-ene, which is unsaturated. It doesn't have on the maximum number of hydrogen atoms that the carbon can hold. It means there's a carbon-carbon double bond or a carbon-carbon triple bond. Let's just highlight where the carbon-carbon double bond is. It's right there. And now we're drawing what the final product would be. The final product for the hydrogenation of 1-butene. I want us to actually see it. All right, so let's put the hydrogens in black, the ones that were added. All hydrogens are identical in this case, but that's what the final product would look like. And this now would be butane, and this is saturated. All right, all carbons are bearing the maximum number of hydrogen that they can bear, and there's no carbon-carbon double bond or no carbon-carbon triple bond. So the saturation was removed by us adding hydrogen. What I want you to do, just go back over what we've gone through. What are the conditions? Find out the conditions for this reaction. The conditions, we'll look at this in our next session when we look at reactions of organic compounds. But this is where we'll call it for today. I did promise that I would send the link. Let me find it. Remember to like, share, and subscribe if you haven't done so. Couple later.